Right now, I mean, if you look around, Fortune 500 companies are spending just millions on these flawless, AI-driven robotic arms.
Oh, absolutely. It's everywhere.
Yeah, and if you look at their shareholder reports, you'd think these manufacturing plants are like sleek, autonomous wonderlands straight out of a sci-fi movie.
Right, like totally lights out manufacturing.
Exactly. But if you actually walk the floor, you'll discover a fascinating, really messy truth. The secret control system keeping those multi-million-dollar factories running isn't some highly advanced neural network.
No, it's really not.
It's usually a guy named Bob standing next to a conveyor belt with a reset button and just a whole lot of anxiety.
Yeah, it is the great industrial illusion of our time.
Yeah.
We are living in this bizarre era where the executive dashboards are, flashing green, celebrating these record-breaking automation metrics,
Right, looking great on paper.
looking perfect. But the operational reality on the floor is incredibly fragile. I mean, the entire system is fraught with hidden friction. It's completely dependent on human intervention just to survive the shift.
Welcome to today's deep dive. We are talking directly to you today, whether you're an engineer, a founder trying to scale a physical product, or just someone who is endlessly curious about how the physical world actually works behind closed doors.
Yeah, we are pulling back the curtain on this massive, largely unspoken crisis in industrial automation and robotics.
Because everyone thinks the future of work is a fully automated factory, but the reality is drastically different.
Totally. And to unpack this gap between the glossy sales brochure and the gritty reality of the factory floor, we are synthesizing some really incredible source materials today.
We've got a heavy stack to go through. We're looking at the World Robotics 2025 Executive Summary from the International Federation of Robotics.
Plus, the World Economic Forum's Intelligent Industrial Operations Outlook 2026.
Right, alongside some deeply researched tech industry reporting. But the piece that really anchors our deep dive today, the one that provides the unvarnished truth, is a set of deep strategic notes from a founder-level systems engineer.
Yeah, this is someone who actually builds these systems from the ground up. And, maybe more importantly, has watched them completely break in production.
The mission for our discussion today is pretty ambitious. We need to uncover why, despite record-breaking robot sales globally and cheaper hardware than we've ever seen, so many facilities still secretly rely on humans as their ultimate safety net.
And we really need to figure out what that means for the future of physical work, for economic productivity, and just how we integrate complex tech into any environment.
Okay, let's unpack this. Let's look at the baseline. According to the visible metrics, like the official reports, that a board of directors might look at what is the current state of automation.
Well, if you read the World Robotics 2025 summary
Okay.
and that WEF outlook, the narrative is incredibly optimistic.
I mean, they're basically cheering, right?
Exactly. The visible symptom is a massive spike in global industrial robot installations. We are hitting record numbers, specifically in the automotive and electronics sectors.
Makes sense.
And driving this is a fundamental economic shift.
Yeah.
The cost of the robot hardware, the actual articulated mechanical arm, has just been dropping aggressively.
So the barrier to entry is way lower. You can buy a highly capable piece of hardware for a fraction of what it cost 10 years ago.
Yes, and executives are aggressively capitalizing on that. I mean, they're looking at this compounding wave of external pressures.
Like the workforce shortages, right?
Severe workforce shortages, supply chain volatility, inflation, cyber risks. They see these increasingly cheap robots, which are heavily marketed as being enabled by AI and machine learning.
And they view it as a silver bullet.
Precisely. They think it's the easy fix.
It makes complete sense from a high-rise office. You have a labor shortage. Just buy a robot. The purchase order is clear. The installation dates are
The
set.
paperwork is done.
If I'm a board member looking at a dashboard, I see that I just approved 50 new robotic cells. The lights are green. We are officially modernized.
But the problem arises when you travel down from that high-rise and stand next to the actual assembly line.
Where it's actually happening.
Exactly. The crucial divergence we have to understand here, and this is a core thesis of our systems engineers' notes, is that installed robots absolutely do not equal installed capacity.
Wait, I'm stuck on something. If the robot is physically bolted to the floor and plugged into the wall, how is that not installed capacity?
Because acquiring the physical asset is really just the beginning of a grueling, often chaotic process. The reality is that automation projects routinely languish for months.
Oh, wow.
Months, sometimes over a year, before they ship a single viable production part. Even when the line is technically declared automated, the robots are often wildly
Or
underutilized.
they're just sitting there.
They sit idle, they fault out constantly, or they're treated as these hyper-fragile glass artifacts that require human babysitters all day long.
Okay, so it's like, say you buy a massive state-of-the-art smart TV, you drop 3 grand on an 8K OLED screen, you mount it on your wall, it looks gorgeous, your living room looks like a cinema, but you don't have Wi-Fi. And your house suffers from rolling blackouts. You own the impressive hardware, it is officially installed, but you have zero usable capacity to actually watch a movie.
That is a phenomenal way to look at it. The hardware is just a node. Without the supporting ecosystem to feed it data, provide stable power, and give it context, it is basically a useless monument.
And in a factory environment, a useless monument is bleeding hundreds of thousands of dollars.
Exactly. It's a massive liability.
But I have to push back here a little bit. We are in an era where software can generate photorealistic video from a text prompt.
Sure.
If AI is so advanced and the physical silicon and motors of these robot arms are so cheap and precise, why are these production lines so brittle? What is actually happening in the machine's brain that causes it to fail so often?
It comes down to a concept called unbounded variability. Standard robotic packages, the ones rolling off the line from major manufacturers, they are spectacular at handling bounded variability.
Okay, so bounded meaning controlled.
Right. If you need a robotic arm to pick up a perfectly uniform, identically weighted steel widget from the exact same millimeter of a conveyor belt and move it exactly 10 inches to the left, 1,000,000 times a day,
It's perfect at that.
the robot will outperform a human every single time.
Because the world it operates in is entirely closed. Every variable is locked down.
Yes, but modern manufacturing doesn't look like that anymore. We are living in a high-mix environment,
You mean things change a lot?
constantly. The stock-keeping units, or LEUs, change constantly to meet consumer demand. Maybe today the line is running blue, matte finish widgets. Tomorrow it's running red, gloss finish widgets that weigh 3 ounces more.
Okay, but how does a color change break a robot? It's just picking something up.
Well, let's look at how a robot actually sees. A robot vision system isn't looking at a widget the way you or I do. It's a camera taking a picture and an algorithm analyzing an array of pixels looking for specific RGB values and contrast lines to identify an edge.
Okay, so it's all math to the robot.
Pure math. So
Yeah.
let's say a cloud passes over the factory skylight. The ambient lighting drops. Suddenly, the shadow on the widget changes.
Oh, I see where this is going.
The pixel contrast ratio drops below the algorithm's confidence threshold. The robot doesn't know it's a shadow. It thinks the physical shape of the object just mutated.
Wow.
So to avoid a collision, it freezes. It throws an error code.
That is wild. It's like how early self-driving cars were flawless on a well-painted highway where the lines are clear and everyone moves in one direction. But the second you put them in a grocery store parking lot with stray shopping carts, pedestrians, and faded paint, the car just stops dead in its tracks.
Yeah, that's spot on.
The parking lot is unbounded variability.
That's the exact mechanism. The real physical world is dirty, things vibrate, parts arrive slightly misaligned from suppliers. Humans are masters of absorbing unbounded variability.
Because we don't even think about it.
Right. If a worker reaches for a part and it's slightly skewed, their brain adjusts their grip in milliseconds without a conscious thought. If the lighting changes, their eyes adjust. Humans can adapt to a completely new skew in an afternoon.
But getting a robot to adapt to that new skew.
It's an agonizing process. It requires weeks of re-engineering. You have to remap the lighting variables, write new edge detection code, redesign the physical grippers.
That sounds incredibly expensive.
It is. You have to test the new safety boundaries and validate the cycle times from scratch. The ROI models that executives use to justify buying these robots are structurally flawed because they assume the transition will be seamless.
They assume the cost of adapting to variability is zero.
Exactly.
And when the robot freezes because a cloud passed overhead, someone has to go over, clear the error, reset the machine, and manually align the part.
Yep.
The human is still the exception handler.
Which brings us to the core bottleneck. The robot arm itself, the silicon, the servos, the gears, is not the problem. It's doing exactly what it was programmed to do.
So what is the actual structural disease then?
The structural disease plaguing modern manufacturing is the socio-technical integration ecosystem.
Okay, let's talk about the math of that integration because the sources bring up a financial reality that just blew my mind.
It's pretty staggering.
For small and medium-sized enterprises specifically, a factory might buy a brand new, highly capable robotic arm for $50,000. That feels like an absolute steal. It feels like the future is highly accessible.
On paper, yeah, it's a great deal.
But then, to actually make that $50,000 arm talk to the rest of the facility, they have to spend $400,000 and 6 months of labor.
It shatters the illusion entirely. People naturally assume that because hardware follows standard learning curves, meaning it gets cheaper and easier to mass produce over time, the entire automation process will also follow a learning curve and get cheaper.
Right, like TVs or smartphones.
Exactly. But socio-technical complexity is stubbornly resistant to learning curves.
Help me understand the mechanism there. Why doesn't it get cheaper to just plug the robot in?
Because every single factory is a unique, bespoke environment. Integration is entirely context-specific. When you buy a robot arm, you are just buying the wrist.
Ah, so it's incomplete out of the box.
Completely. You still have to pay for the peripheral engineering. Someone has to custom machine the end effector, the physical hand of the robot.
Right.
If it's a vacuum gripper, someone has to route pneumatic lines, install suction cups, and wire pressure sensors. Then you have to build the custom vision pipelines, design the physical safety cages, pass rigorous OSHA certifications, and commission the system on-site.
And it's not like they are dropping these robots into pristine tech labs in Silicon Valley. These are active, dusty, older factories.
That is the massive hidden iceberg, legacy infrastructure. You have factory managers trying to drop modern ROS-enabled robots into environments running conveyors and networks that were built 20 or 30 years ago.
So let's pause and define that for a second, because this is where the clash of eras happens. ROS stands for Robot Operating System, right?
Correct. ROS is a highly complex open-source middleware used to control modern robots. It deals with incredibly complex data.
Like what kind of data?
Things like 3D spatial mapping, complex kinematics, megabytes of data streaming per second.
Okay, and what are the older factory systems running on?
They run on PLCs, programmable logic controllers. A PLC is basically an industrial computer from the 1980s or 90s.
So pretty old school.
Very old school. Think of a PLC as a highly reliable metronome. It operates on simple 24-volt electrical logic. It just ticks away, scanning inputs every few milliseconds.
Is sensor A active? Yes. Okay, turn on motor B.
Exactly. It is incredibly dumb, but it is bulletproof and perfectly reliable.
Here's where it gets really interesting. I see the collision coming. You are basically trying to drop a Ferrari engine into a rusted 1990s station wagon.
That's a great analogy.
The engine isn't the problem, but the transmission will instantly blow. The physical and digital layers fundamentally cannot shake hands. You have ROS, which is trying to send massive, complex paragraphs of data about 3D space, trying to talk to a PLC that only understands simple yes-no electrical pulses.
Right.
The older network literally cannot process the bandwidth or the vocabulary. The robot is blamed for being brittle, but the real constraint is the interface debt.
It is a profound interface debt. Modern industrial networks use protocols like EtherCAT or Profinet, which force deterministic to the microsecond communication so the robot doesn't, crash through a wall.
Which is important.
Very. But a 20-year-old conveyor belt system does not speak EtherCAT. It simply cannot communicate. So to make the $50,000 robot work, the factory has to rip out and retrofit the old wiring, upgrade the PLCs, install new network switches, and write custom translation software.
And suddenly your $50K purchase is a $500,000 nightmare.
Exactly. This is what the systems engineer in our sources brilliantly terms technical debt, expressed as organizational paralysis.
Organizational paralysis.
Wow. The physical and digital systems can't talk to each other, so the entire organization just freezes up in confusion and cost overruns.
Which brings us to a massive realization. When that metaphorical transmission blows on the factory floor, when the system freezes and the lines stop moving, it's not just lines of code failing in a vacuum. Someone has to absorb that failure. Let's look at the human cost, the people actually standing next to these machines.
This is perhaps the most overlooked and profound consequence of the integration choke point. We are witnessing a massive skills mismatch that generates a culture of sheer terror rather than empowerment on the factory floor.
Fear, that's a strong word.
But it's accurate. Think about the maintenance teams in these facilities. These are highly skilled veterans. They've spent 20 years turning wrenches, lubricating bearings, and fixing mechanical systems.
Right. These are the folks who can listen to the hum of a line and tell you exactly which gear is wearing out just by the pitch of the vibration. They have this deep physical intuition about the factory.
And suddenly, a pristine white robotic cell is dropped onto their floor. Management tells them, hey, this is the new system, keep it running.
Good luck.
Yeah. These mechanical experts are now expected to debug ROS software stacks. They're expected to troubleshoot edge AI processing units and complex digital vision pipelines.
Which is an entirely different universe of engineering. You're asking a master carpenter to suddenly perform network cybersecurity.
It creates an immediate psychological wall because the local teams lack these hyper-specific modern software skills. They cannot effectively manage the new systems.
So what happens?
As a result, the robot becomes an untouchable artifact. The prevailing attitude becomes, once the outside contractors finally get the machine to sort of work, do not breathe on it, do not clean it, do not look at it funny.
Because if it breaks,
Right, because if it throws an error code, we have absolutely no idea how to fix it. The system just freezes.
it becomes a fragile museum piece that just happens to build car parts.
Exactly. The knowledge required to run the factory essentially evacuates the building. It concentrates outside the plant, residing with external vendors, software engineers, and specialized integrators.
Taking the power away from the workers?
The local maintenance teams lose their agency. They are relegated to being nervous bystanders in their own workplace.
I want to share a story from the engineer's notes that really grounds this abstract technical discussion in something deeply emotional. We'll call this the grenade story.
Ah, yes. This is a powerful one.
This founder-level systems engineer was working on a project years ago, consulting for a facility. He was walking the floor to observe the current, fully manual process. He watched these factory workers handling live grenades.
Just let the gravity of that sink in. It's not widgets or car parts, live explosives.
The engineer noted that the workers moved as if they were holding their breath. The tension in the room wasn't just palpable, it was a physical weight pressing down on everyone.
I can only imagine.
Every single movement had to be perfectly calculated, perfectly calm, because in that environment, a single error of bounded variability, a slip of the finger, a sneeze, a momentary distraction, was catastrophic.
Is the ultimate high-stakes environment. The cognitive load on those workers must have been staggering.
So the engineer built a robotic system for that specific line. But what's so striking is his core motivation. He didn't build it for innovation.
Or for efficiency.
Right. He didn't build it so the company could brag about automation metrics on a dashboard or increase throughput by 4%. He built it for fear. He wrote that the real ROI, the actual return on investment, wasn't a financial metric.
How was it?
The ROI was a worker getting to go home at the end of their shift, sitting down at the dinner table and being able to say, I'm safe tonight.
If we connect this to the bigger picture, that is a profound philosophy. Good technology at its absolute core should reduce risk and restore human dignity.
Absolutely.
It should absorb the tasks that are dull, dirty, or dangerous, allowing humans to operate safely and use their cognitive skills for higher-level problem solving.
It shouldn't just be about replacing human labor to shave a few cents off a unit cost on a spreadsheet.
But look at what the current broken state of automation is doing. When you dump an AI robot into a legacy system without proper integration, you're actively violating that implicit social contract.
How so?
Instead of reducing risk, the current system is externalizing the risk back onto the people on the floor.
Wait, I see what you mean. Because the robot is brittle, and because it fails when the lighting changes or a part is misaligned, the human worker is forced to constantly jump in.
Exactly. The worker becomes the default, unpaid exception handler for a fragile machine.
That's so backwards.
They're incredibly stressed,
Yeah.
they're undertrained for the software they are dealing with, and they spend their entire shift waiting for the inevitable alarm buzzer to go off. Instead of being liberated by the technology, they're subjugated by its brittleness.
Let me play detective here for a second. If the workers are miserable and stressed, and the factory owners are bleeding cash on $500,000 integration overruns, why does this illusion persist?
It's a great question.
If nobody inside the four walls of the factory is winning, someone else has to be making an absolute killing. Who actually benefits from this fog?
Unpacking the incentives reveals the structural rot of the industry. The deep dive into our sources points the finger directly at two groups who profit immensely from the obscurity of these integration failures.
Okay, let's name them.
First, you have the hardware vendors.
The companies making the sleek white robotic arms and the shiny brochures.
Yes, they are highly incentivized to sell the easy automation narrative. They market the hardware as infinitely flexible, plug-and-play, and AI-enabled.
Right.
But crucially, look at their business model. It allows them to sell the capital hardware without taking any ownership of the downstream outcomes.
Oh, wow.
The moment that robot arm is unboxed on the factory loading dock, their primary revenue is secured. They do not have to absorb the pain of making their modern arm talk to a 1990s PLC.
It's the ultimate wash your hands scenario. We sold you a perfect, mathematically flawless arm. It's not our fault your factory is too messy to use it.
Exactly. The second group benefiting from this mess are the system integrators.
The specialized contractors, the people whose entire job is to translate between the USB-C cable and the cassette tape player.
And they charge premium, six-figure consulting and engineering fees precisely because they hold a monopoly on making these disparate systems communicate.
Right, because nobody else knows how to do it.
What we are witnessing is a classic power law scarcity dynamic. As more and more firms rush to automate driven by boardroom panic over labor shortages, the limited pool of truly experienced integrators and hybrid mechanical software engineers is stretched incredibly thin.
It's basic supply and demand. The supply of experts who understand both ROS and legacy PLCs is tiny, but the demand from Fortune 500 companies is skyrocketing.
So prices rise exponentially. Timelines extend from a few weeks to many months or even years. And here is the truly perverse incentive.
Let's hear it.
The integrator's leverage actually increases as long as the complexity remains illegible to the factory owners.
Wait, really?
Yeah, if the plant manager doesn't understand why the robot vision system keeps freezing, the integrator can name their price to come in and fix it.
That's wild.
The economic scarcity has migrated from the capital goods, the robots themselves, to the highly specialized human knowledge required to string them together.
It's a brilliant, if entirely parasitic, business model. Obscurity protects the incumbents. As long as the integration layer is a black box of proprietary code and complex network protocols, the factory is a hostage. They are completely dependent on outside help.
And the ripple effects are massive.
Yeah.
The people absorbing the pain of this obscurity are the operators on the floor dealing with the daily stress. It's the small and medium enterprises who can't amortize a $400,000 integration bill across multiple sites the way a massive conglomerate can. And ultimately, it's you and I, the end consumers, who deal with supply chain fragility, shortages, and price hikes when these brittle factory lines inevitably go down.
So, if I'm understanding this correctly, are factories essentially buying expensive monuments to their own lack of ownership? Is the control point completely outside the plant?
In the vast majority of modern automation projects, yes. The control point currently lives with outside vendors, but recognizing that harsh truth is the first step to reclaiming it.
Right.
If we understand that the real bottleneck isn't a lack of AI or a lack of advanced silicon, but rather a failure of socio-technical coordination, we can pivot to the solution. How do serious founder-grade operators actually take back their factory floor using first principles?
Let's get into the playbook. This is by far the most compelling part of the systems engineer's notes because it entirely rejects the Silicon Valley hype cycle. The solution isn't to buy a more advanced AI model or a shinier robot.
Definitely not.
The playbook outlines a series of cheap, bootstrapped moves that compound.
It demands a complete redefinition of what a control point is. The sources argue forcefully that the true control point is not the robotic hardware, and it is certainly not the executive dashboard.
So what is it?
The true control point is process legibility combined with local stewardship.
Process legibility and local stewardship. Let's break down the specific, actionable steps the sources provide to achieve that. Let's spend some real time on this because this is the antidote to the illusion. Step 1, the one-cell truth audit. What does that actually look like in practice?
It looks shockingly low-tech. Before a factory manager even thinks of picking up the phone to call a robot vendor, they must pick one single manual workstation on their floor and map it entirely on paper.
On paper.
On paper.
Oh.
They need a clipboard and a stopwatch. They must track the exact cycle times, the physical variability of the incoming parts, and absolutely every possible exception or failure mode that happens during a shift.
So no software simulations allowed, just standing there watching the reality of the work.
Because the insight here is brutal but undeniable. If you cannot make a physical process entirely legible to a human observer, a machine will absolutely fail at it. You cannot automate a process that you cannot accurately describe.
I can imagine the pushback a manager would get doing this, but it's the only way to expose the hidden heroics of the human workers. A manager might think a task is just put widget A into box B.
Right.
But if they stand there with a stopwatch, they realize, oh, wait, Bob actually taps the widget twice against the table to align the internal spring before he scans it.
Exactly.
The management never noticed the double tap. But a robot won't know to do that unless it's explicitly mapped. And without that double tap, the part fails inspection down the line.
That is the exact kind of tacit knowledge the audit is designed to uncover. Once you have that truth, you move to step 2. Boundary specs over feature wish lists. When companies currently buy robots, they write these absurd aspirational wish lists.
We want a robot that can handle 20 different SKUs, use AI to inspect for microscopic defects, automatically reorder its own parts, and maybe sing happy birthday to the floor manager.
It's a recipe for scope creep and integration hell. A serious operator does the opposite. They write a strict boundary spec. Instead of listing what the robot should do, they define exactly what the robot must not do. They treat the software integration like a strict mechanical drawing.
Give me an example of that. How do you define what a software program shouldn't do?
You define the absolute physical constraints. If the robot is placing a windshield onto a car frame, the boundary spec dictates the absolute maximum force the arm can exert, say, 15 newtons.
Okay.
If it exceeds 15 newtons, it immediately halts so it doesn't shatter the glass. You define the exact speeds it is limited to. You define the spatial 3D zones it is never allowed to enter to prevent collisions with human walkways, and you explicitly list the SKUs it is forbidden from handling.
You are building incredibly thick digital walls around the machine.
Because constraints reduce integration ambiguity. When the system integrator knows exactly what the machine will never be allowed to do, they don't have to write bloated, complex exception-handling code for impossible scenarios. Safety and reliability improve instantly when the boundaries are rigid.
That makes total sense. Okay, step 3. Boring stability first. This seems like it requires a massive ego check from the executive team.
It runs counter to every marketing instinct in the corporate world. The temptation is always to automate the most complex, high-mix, impressive-looking task first to prove how innovative the company is.
Right. They want to make a slick viral video for LinkedIn showing a robot doing a backflip while juggling car parts.
But you are not buying a demo reel. You are buying predictable throughput. The playbook insists that you automate the most boring, stable, highly repetitive, low-variance task you have. You want to prove that the fundamental integration works, that the ROS network can talk to your legacy PLCs, and that the machine can run 24 hours a day, 7 days a week without throwing a single fault code. You build internal organizational trust with boring stability before you ever attempt to scale up to complex, high-mix tasks.
Which brings us to step 4, and this directly addresses the human element, the terror of the untouchable artifact we talked about earlier. Local robot stewards.
This is how you reclaim agency. The playbook dictates that you cross-train 2 floor operators per robotics cell. Not external engineers, not IT specialists from corporate, but the actual mechanical maintenance people who already work on that line.
You train Bob.
You train Bob. You teach him how to handle basic system faults. You teach him how to safely reset the machine after a hard stop. You teach him how to program simple teach points.
Wait, what does that mean? A teach point?
Most modern robots come with a teach pendant. It looks like a large, ruggedized tablet with a joystick. If the robot needs to learn a new position to pick up a part, an operator can physically drive the robot arm to that exact spatial coordinate using the joystick and hit a button to record that point in space.
Oh, that's pretty intuitive.
It doesn't require writing lines of code, it requires physical intuition.
Which is exactly what Bob has. He knows exactly how the part should be oriented.
Exactly. We need to stop treating automation like a sacred priesthood reserved only for outside vendors who charge $300 an hour to dial in remotely. Give the agency back to the workers.
Yeah.
If Bob knows how to clear a fault, and he knows how to use a teach pendant to adjust a misaligned pick point, Bob isn't afraid of the robot anymore. It ceases to be an untouchable artifact. The robot becomes his tool, an extension of his own mechanical expertise, rather than his replacement.
It brings the control point back inside the 4 walls of the plant, and it restores the dignity of the operator. That is brilliant. Finally, step 5. Measure time in productive motion.
This is the metric that permanently replaces the vanity dashboards. You treat every single robot cell as its own micro P&L.
Okay. Profit and loss.
Right. The key metric for the executive suite shouldn't be, is the robot turned on? The metric is the robot physically moving product forward?
Because if the robot is sitting idle, or if it is faulted out with a blinking red light, waiting for an external programmer in another time zone to log in and diagnose the vision system.
Then it's not an automation success. It is an integration failure. You are hemorrhaging money every single second that machine waits for an exception handler.
Wow.
By religiously tracking time and productive motion, you make the integration failures painfully, undeniably visible to everyone in the company. You force the organization to solve the real bottleneck rather than hiding behind a green light on a software dashboard.
So what does this all mean? When I look at these 5 steps, the strict boundary constraints, the brutal honesty about the physical process, the focus on unglamorous stability, and empowering the local user, it immediately reminds me of the design philosophy of Dieter Rams.
Dieter Rams, the legendary industrial designer at Braun.
Right. The source notes actually mention him in relation to visual engineering, and the parallel is striking.
His work deeply influenced the design of modern consumer electronics, most notably Apple.
Right. His core principles were all about less but better. He believed that good design is inherently honest. It doesn't make a product appear more innovative, powerful, or valuable than it actually is.
That sounds exactly like what we're talking about.
Good design is unobtrusive. A product should act like a tool, not a decorative piece of art. And most importantly, the materials must act like what they are. You cannot gloss over a messy, highly variable factory floor with a shiny white robot arm and pretend the mess has magically disappeared.
Right.
You have to design the entire system to honestly handle the reality of the environment.
It's a philosophy of profound restraint and clarity. And applying that restraint to industrial automation, acknowledging the limitations of the technology and honoring the physical reality of the factory is the only way to actually reclaim the control point from the fog of complexity.
We've spent this entire deep dive inside the factory walls, talking about conveyors, PLCs, ROS networks, and robotic cells. But as we wrap up, I want to address you, the listener, directly. Why should you care about any of this if you don't run a manufacturing plant?
It's a fair question.
Why does the integration choke point matter to your life? Because we are all, right now, being aggressively sold the exact same automation and AI narrative in our own daily lives.
We absolutely are. The identical dynamics we just discussed on the factory floor are currently playing out in the software tools we use at work, our personal workflow automations, and our smart home technologies.
Think about it. You get targeted by an ad for an AI tool that promises to automatically sort your inbox, draft replies, and manage your calendar perfectly.
Or you buy a complex smart home setup that promises to run your lighting, security, and climate controls seamlessly.
And the consumer dashboards look incredibly sleek. The promises of saving time are huge.
But the core truth we uncovered today remains exactly the same, regardless of the scale. Technology does not magically erase variability.
It really doesn't.
It doesn't make the messy, unpredictable details of life disappear. It just moves the bottleneck.
If your smart home system breaks because your local Wi-Fi drops, or if your automated AI workflow forwards the wrong, highly sensitive email to your boss because it didn't understand the nuanced context of a joke, who has to step in and frantically fix it? You do.
It's the exact same problem as the robot on the factory floor.
Well,
If you don't own the exceptions, if you haven't meticulously mapped out the boundaries and the failure modes of the tools you use, then you don't actually own the system.
yeah.
You just become the unpaid, highly stressed exception handler for a brittle piece of software. The technology was explicitly sold to free up your time, but instead it just externalized the integration risk directly onto your shoulders.
So here's a final provocative thought for you to mull over as you go about the rest of your day. Take a hard look at the automated systems in your own work or your own personal life. The productivity apps, the morning routines, the smart devices.
Yeah, look closely at them.
Are they actually granting you predictable throughput? Are they genuinely saving you time and restoring your mental energy? Or have you just secretly become the stressed out integration layer, desperately holding a fragile, over-engineered system together? What is your personal boundary spec for the technology you allow into your life?
That is the question we all need to be asking.
We started today standing on that pristine cinematic glass walkway, looking down at the illusion of perfect automation. But the real work, the true engineering, is getting down on the gritty floor, grabbing a stopwatch, and understanding the mess. Thanks for joining us on this deep dive. Question the hype, look for the real bottlenecks, and make sure you are always the one holding the control point.